the organizers for giving me the opportunity to speak in this distinguished seminar. And what I will tell you about is a joint work with Eva Bayer-Fluckiger and Raman Parimala. So there has been, I should say, I think I recall 2 talks in the seminar at least about the Grothendieck and Serre conjecture, one by Stavrova and one by Chesnavichus. And I think this one will be somewhat different in the kind of type of result. So let me start by recalling the Grothendieck and Serre conjecture. Although I think everybody are familiar with it by now. So R will be a semilocal regular domain, and K will be its fraction field, and G will be a reductive group scheme over R, by which I mean that the morphism G to spec R is a flat of finite presentation, and the geometric fibers are connected reductive groups. So, for example, well, in this seminar, probably everybody know maybe GLN, SLN, SO of some quadratic form, Q over R, PGLN, and so on. So the Grothendieck and Serre conjecture so the original early versions of this conjecture appeared in 1958 by Grothendieck and Serre, and then Grothendieck gave a more general statement in 1968. It says the following: so let X be a G-torsor, then if our torsor X has a K rational point, then it has a rational point over R. So it has an R point. And just to demonstrate what kind of what a statement like that can give. So let's just consider 2 quadratic forms Q and Q prime from R to the N. So this would be regular quadratic forms. The Gram matrix has to have an invertible determinant. And let us take G to be the orthogonal group of Q. So it is not connected, I'm cheating, but that is not a problem actually. Just for the sake of demonstration, this will suffice. And I can take X to be the isometries between Q and Q prime. So that is a scheme, and it has a G action by precomposition. So X times G is just X composed with G on the level of section. So this is a G-torsor. Then if I apply the Grothendieck and Serre conjecture, if it holds for the orthogonal group of Q, then this would imply that this X has a K point if and only if it has an R point. But this is the scheme of isometries from Q to Q prime. So it would imply that if Q and Q prime become isomorphic over K, then they would become isomorphic over R. So they would already be isomorphic. So here I should say, okay, this is not connected. But you can easily reduce it to the case of SO. But anyhow, the Grothendieck and Serre conjecture is a kind of, I would say, factory for statements of this kind, that you have 2 objects isomorphic over the fraction field, and then they are already isomorphic. Okay, so I should probably let me say some words about what is known, what is the status of the conjecture, and I should say that quite a lot is known. I would not be able to survey everything, There are people here in the audience who have worked on the conjecture. So let me give a very partial survey on the conjecture. And usually, so either you limit the ring or you limit the group. So okay, so here are examples where you only limit one of them. So the conjecture is known when G is a torus. And this is a result of Kolyatelin. And Sansuk from 1978, I think. It is known when R contains a field. And this is by Fedorov and Panin when K is infinite, and by Panin when K is finite. And this is very recent. I don't remember the exact dates, but I think these are the numbers. And this is also known when the dimension of R is 1. So I allowed here R to be semi-local. So this is a bit more general. Usually it's conjectured for local rings. And the case where R is local is due to Nisnevich in 1984. And this is when R is a DVR. And recently, the general case of semi-local Dedekind domain was done by Guo, Ning Guo in 2020. And there are many, many, many more results, which I will not be able to survey. And what I would like to tell you about today is that, so this is the result with Eva Bayer-Fluckiger and Raman Parimala, is that there are some more cases which are correct. So the Grothendieck Serre conjecture holds when. So I have to give some restriction on the ring and some restriction on the group. And I will give 3 sets of such restrictions. So the first restriction is it holds when the dimension of R is less than or equal to 2. And G is a form. So our reductive group scheme is a form of GLN, SON, or SP2N, the symplectic group. So those are, if you like, those are my classical groups, very, very classical. It also holds when the dimension of R is at most 4, and G is a form of GL2N plus 1. So maybe a unitary group of Azumaya algebra within a unitary involution. And there is also a third case, which is just me, when the dimension of R is less than or equal to 3, and G is a form of SON or SP2N plus some assumption, which I will touch later. So this I will clarify this later. And let me just recall what is a form, because I used this word 3 times now. So what is a form of a given group scheme? So just a remark. Let G and H be group schemes over R. G is a form of H if those 2 group schemes become isomorphic over some faithfully flat étale algebra. So they become isomorphic after some étale covering. So if there exists a faithfully flat étale R algebra S such that GS is isomorphic to HS. And what is so special about those types of groups that you see here, GLN, SON, and SPN, which feature in all of these, is that the forms of these groups can be described by means of Azumaya algebras with involution. And then we use techniques about, we use hermitian forms, and we use the Gersten-Witt complex to establish this result. So let me just, so I will need to recall what are Azumaya algebras with involution. So henceforth, 2 is going to be assumed invertible in the base ring, and I will write Kp for the fraction ring of R mod P if P is a prime ideal. And so before I can tell you what is an Azumaya algebra of involution, I think many of you already know, but I would like to recall anyhow. So let me recall what is a central simple algebra of involution in the sense of the book of involution. So if K is a field, then a central simple algebra with involution. So is a pair a sigma such that, well, A is a finite dimensional K algebra, and sigma from A to A is a K involution. So I require the involution to be K linear, and one of the following. Hold. So either A is simple, so it's simple Artinian, and I do not require its center to be K. I require that the sigma fixed part of A is K. Okay, so that's just notice that this difference. I do not. The center could be a quadratic extension, or there is another option. I need to allow the center to be K times K. If this happens, then this is isomorphic to A sigma is isomorphic to B times B opposite, and here I put the so-called exchange involution. Yx op. This is kind of a degenerate case with the B central simple algebra over K. So this is a central simple algebra with involution in the sense of the book of involutions. And it is good to just to notice. Let me set the notation. Let U of A sigma, if A is a central simple algebra of involution. Okay, so so A sigma is a central simple algebra with involution over K, and let us put U of A sigma. This will be the group scheme over K, cut by the equation sigma A times A equals 1 in A, when I regard A as an affine space. And that it's worth noting. So what does this have to do with all the group schemes I mentioned earlier? So the center of A, there are two options. It is either a K or it is a quadratic tau K algebra. So either this is a quadratic field extension or it is K times K. And here I have two options. Either sigma is orthogonal or sigma is symplectic. And in this case, this group, which I called UA sigma, is a form of O of ON. And here, this group is a form of SPN. And here, then, when the center is not K, when it is a quadratic étale K algebra, then sigma is called unitary. And then this group scheme, which I defined, is a form of GLN, where here n is the degree of A. It is roughly the square root of the dimension, or maybe I should say rank, because center might not be connected. of the rank of A. And just notice that if I take the neutral connected component of this group is a form of, well, either SON, so here I have SON instead of ON because I take the neutral connected component, or SPN or GLN, and all forms of these groups are obtained in this manner. So here I'm still working over the field K. Any questions? So now that we have talked about what is happening over a field, so let me generalize and globalize it to a ring, and I will leave it. So it is very. It can also be done for schemes, but let me do it only for rings. So what is an Azumaya algebra with involution? So definition. So let R be a commutative ring, then an Azumaya algebra with involution over R is an R algebra with an R involution a sigma, such that what do I require? The first thing is that A is a finitely generated projective R module. If you work over schemes, you have to require that this is locally free instead of finite rank. And the second thing is that for every prime P of R, if I specialize my algebra to the residue field at P, so this is just A tensor KP and sigma tensor E KP, and the tensor is always over R. This is a central simple algebra with involution in the previous tense over KP. And this is the definition of an Azumaya algebra with involution. I should say that there are many other equivalent definitions. And just a remark, if R is connected, then the type of sigma Kp does not depend on P. So we say that sigma is orthogonal or symplectic or unitary accordingly to the type of just at some prime. It doesn't matter which one. Maybe I should give at least one example. I don't know. I think everybody are familiar with central simple algebras with involution, but let me give just one example. So let's take some two invertible elements. Then you can form the quaternion. You can do the quaternion algebra construction in the usual way. Just joining two generators I, J, and subject to these relations. And just take the involution sigma determined by sending I to negative I and J to negative J. So A sigma is an Azumaya algebra with a symplectic involution over R. Just one example, I think. And actually, if R is semi-local, then this is all the examples of Azumaya algebras of with involution, symplectic involutions of degree 2, which you have. And I should say again, so if I take the group of unitary elements, so now this is a group scheme. This is a group scheme over R, the group of elements satisfying sigma A equals 1. This is a form of one of the following group, either GLN if sigma is unitary, or SON if sigma is orthogonal, or SPN if sigma is symplectic. And this exhausts all these forms, this description. So now I can restate the theorem which I have written. Was it theorem 1? I can't remember. Now it's going to be theorem 1. So now I can give a more precise statement. So R is a regular semilocal ring, and A sigma will be an Azumaya algebra with involution over R. And then the Grothendieck-Serre conjecture holds for the neutral component of the group of sigma unitary elements in A if one of the following holds. So either the dimension of R is at most 2, or the dimension of R is at most 4. And I can actually say that the index of A is odd. The index of A is so you just take all the Brouwer equivalent representatives of A, and you just take their degree and you compute the GCD. Because we assume R is a semi-local, there is actually a representative in the Brouwer class of that degree. So if the index is odd, then this is the Grothendieck-Serre conjecture holds for this group. And finally, I can give a precise statement of the third part. If the dimension of R is at most 3, and sigma is orthogonal or symplectic, and the index of A is 2, then this is also true. So A is essentially a quaternion algebra, but or equivalent, Brouwer equivalent to a quaternion algebra. So this is really the result which I would like to tell you about today, restated. Any questions so far? Okay. So we approach this using the Gersten-Witt complex, so which I will now explain. So this is almost the third introduction. This is the Gersten. Let me talk about the Gersten-Witt complex. And rather than giving it a precise definition, let me first give an example, which I hope many of you know. So this is kind of a toy example of this complex. So let us consider simply a discrete valuation ring with fraction field K and the uniformizer pi. And let little k be the residue field. Then there is a very famous result of Springer, which says that there is an exact sequence of Witt groups, which goes as follows. So we start at the Witt group of R. So I take regular quadratic forms over R, under orthogonal sum, modulo hyperbolic forms. I don't have to worry about metabolic forms because 2 is invertible. And this goes to the Witt group of K, and it goes to the Witt group of little k. And this here is essentially base change from R to K. And here sits what is sometimes denoted delta pi and is known as the second residue map, which is defined as follows. So I have a Witt class of a quadratic form over K. So I can always diagonalize it. And so I can write it as alpha 1 up to alpha n, but I can, by clearing squares, I can make it so that I have alpha 1 to alpha r, and then I have pi beta 1 to pi beta s, with alpha 1 up to alpha r and beta 1 up to beta s. They're going to be units in R. So I can always do that because the valuation here, the valuation is going to be even. So I'm going to clear an even power of pi, and here the valuation will be odd. So I'm going to clear powers of pi until I get this. And this is defined to be simply the Witt class of the quadratic form. I just reduced beta 1 to beta s modulo pi, and this is in the Witt group of little k. And this is the, well, it can be shown that this is well defined. And it's almost immediate to see that this is exact in the middle. You can see that if the quadratic form comes from R, then it can be diagonalized, and so you see that if it comes from R, then it goes to 0 here, and if it goes to 0 here, okay, that maybe that if it goes to 0 here, then it can be shown that it comes from R. So this is a special case of a Gersten-Witt complex, and in general, there has been a conjecture. So in the early 80s, William Pardon conjectured the following. So Pardon, in 1982, he conjectured that there should be a higher dimensional analog of this exact sequence for rings, for local rings of higher dimension. So here I have a one-dimensional ring. So what Pardon conjectured is that for every regular, every regular domain, of, although it's not strictly necessary, R, there is a cochain complex taking the following form, so-called a Gersten-Witt complex. So it takes the following form. We start with 0, and we have the Witt group of R goes to the Witt group of K, and then comes the following term. We take all the codimension 1 primes, and we consider the Witt groups of their residue field. And the next term will be all the codimension 2 primes, and we take the sum over their Witt groups. And this continues, and eventually it will stop as we reach the dimension of R. After that, it will vanish. And and he also conjectured that maybe moreover, this is exact if R is local. And here, this map should be base change. And these maps should be second residues in the sense of Sprenger. And the next maps are more delicate. It's more difficult to define them, and this is the challenge in this problem. And this, of course, resembles the Gersten complex for K groups, which is why this is called the Gersten-Witt complex. So let me tell you about what is known. So Pardon himself, some of this is unpublished in 1984, and some series of preprints he constructed such a complex. Let me denote this by GWR, and it proved the exactness if R is local and the dimension of R is at most 4. And a lot of time has passed, and then Balmer and Walter came in 2002 and gave another construction. Which is based on triangulated hermitian categories. And the same result, exactness, they got the same proof of the exactness. And same result. And Balmer and Pretty in 2005, improved the exactness. The exactness holds, so this is exact for our semi-local, and the dimension of R is at most 4. And I should say also when R contains a field, and I will say that.
May I ask you a short question?
Yes, please.
In this theory of known results about the Gersten-Witt, so is it the case that in all cases the assumption is this R contains a field, or it's not?
So I was about to say that if R contains a field, then this is a result of well, of yourself together. So the exactness holds. Well, I should say semi-local and contains a field. So the exactness holds. This is due to Stefan Giele, and let me. Okay, so this is Balmer and Giele and Panin and Walter. And also they are basing on results of Walter. And there are a few more additional results. There is this is holds if R is unramified by Jeremy Jacobson. But I should say, what I want to say now is that Stefan Giele, in 2 preprints by from 2007 and 2009, he generalized it to Azumaya algebras with involution over R. So if A sigma is an Azumaya algebra with involution over R, so we have a Gersten-Witt complex. It takes the following form. So it looks like that. So we have the Witt group of the hermitian forms over A sigma. Then we go to the fraction field, and then we add the codimension 1 primes. And here I have to take A kp sigma kp. I have to base change, and it continues with the codimension 2 primes. What Giele showed, eventually he showed in 2013, he showed immediately that if R is of geometric type over a field, then this is exact. But if R is local and contains a field, then exactness, then this is exact. Okay. So what does all of this have to do with the Grothendieck and Serre conjecture? So the point is that there is the following proposition. I'm not sure how known it has been, but it appeared in a paper of mine from 2018, still on the archive. And the connection to the Grothendieck and Serre conjecture is the following. So it says that if the first map in this Gersten-Witt complex, the map from A sigma. Okay, I should make some assumptions before I state this. So R is a regular semi-local domain. And A sigma is an Azumaya algebra with the involution. If the restriction map from A to, if the base change map from the Witt group of A sigma to the Witt group of A k sigma k, where k is the fraction field of R, if this is injective, then the Grothendieck and Serre conjecture holds for the group scheme of sigma unitary elements in A, and you have to take the neutral component in case the involution is orthogonal. So you actually, if you can prove that the Gersten-Witt complex is exact, you will get the Grothendieck and Serre conjecture for that Azumaya algebra. I should say that there is a converse. If you do it for all forms of SPN, GLN and SON, then you actually have a converse. So the map on the Witt groups would be injective for all Azumaya algebras with involution. So it's essentially equivalent. So I should say that maybe you should say the case A equals R was known since is due to Collier-Telen. From 1979. So this, and I think that what was known in 1979 was enough to prove this, but then this was not observed. I'm not sure why. So now I can give you maybe a second theorem. What we actually prove is that the Gersten-Witt complex is exact, the entire complex, not only the first map is injective. So let A sigma be an Azumaya algebra with involution over a regular semilocal ring R, which is not required to contain a field, then the Gersten-Witt complex of A sigma is exact if one of the following holds. So if the dimension of R is at most 2, or again, the dimension of R is at most 4, and the index of A is odd, or third condition, the dimension of R is at most 3, and the index of A is 2, and sigma is orthogonal or symplectic. So this is actually, the main result. And I should say that Stefan Gille independently got similar results. So independently, Stefan Gille proved that the Gersten-Witt complex of A sigma is exact in degrees. So this is degree -1, this is degree 0, this is degree 1, because this is the one here. So in degrees -1, 0, and 2, if R is two-dimensional. So this is actually enough to derive the Grothendieck and Serre conjecture in the, for forms of GLN, Spn and SOn in dimension 2. Although so I should mention this independent work. This was done roughly at the same time. Okay, so in the remaining time, I would like to tell you about the proof of this theorem. Any questions? Okay. Okay. So I just transformed it into something which is seemingly more difficult. And so the proof. Maybe this is part 4, I guess. Proof of, or maybe about the proof. The proof of theorem 2. So the ingredients for this proof are the following. So we have not yet another definition of a Gersten-Witt complex, a new construction for a Gersten-Witt complex of A sigma. It is isomorphic to Stefan Gille's construction and to Balmer's construction when A is R. We show it for the Balmer construction, but we do not need it for Gille's construction. So this is isomorphic to Balmer-Walter and Stefan Gille's construction. And the second ingredient is an 8-periodic exact sequence of Witt groups, which I will tell you about in a moment. And the third ingredient is a version of Springer's theorem for about odd rank extensions. Which says that essentially, if I I can just state that if S over R is the odd rank and the tal and R is semi-local, then the map from the Witt group of A sigma to the Witt group of AS sigma S is injective. So, and these are the ingredients, and the broad idea is to induct on the degree of the algebra A. And the base case is when the degree of A is 1, namely that when A is R. So this is known by Balmer and Walter, because they showed it up to dimension 4. So we're kind of safe. I will tell you mostly about this, but we sort of, in all of these cases, we sort of induct on the degree, and Balmer-Walter is our base case for the induction. So now I would like to tell you about this 8 periodic exact sequence, and this is the device which allows us to induct on the degree. So I'm going to, I have written it in advance. Okay, so don't look here just yet. Look at this. So this is there is an 8 period. We're interested in the Witt group of A sigma, and it fits into this 8 periodic exact sequence. So let me unfold it one piece at a time. So actually, the setup here is that R can be any commutative ring. We will care about the case where it is a semi-local ring eventually. A sigma will be an Azumaya algebra with involution. And I'm assuming that I'm given 2 elements, lambda and mu, which are invertible in A. And they satisfy quaternionic relations relative to the involution sigma. So mu sigma is negative mu, and lambda sigma is negative lambda, and they anti-commute. So here this is like the quaternion relations. In addition, I assume that lambda squared is central in A. And then once I have this data, I define another set of data, which is another Azumaya algebra, which is B. It is the centralizer of lambda in A. It is Azumaya over its center. And the key point here is that its degree is half the degree of A. So it has to be checked. It can be shown. One has to do this carefully. The involution sigma restricts to B, and I call this restriction tau 1. And you can also take the inner automorphism, which is given by conjugation by mu to the negative 1, and compose it with sigma. And this restricts also to B, and you get another involution, which I call tau 2. So explicitly, it is given by this formula. So I have 2 involutions on B. So now we have all the ingredients. So now we have an exact, not an exact, we have a cochain complex, a periodic chain complex of Witt groups. So we start here, we go to the Witt group of B and tau 1 of Hermitian forms. The -1 here means skew Hermitian forms, namely -1 Hermitian forms. And it goes like this, and you have some kind of an anti-symmetry if you look at this. So there is some kind of an anti-symmetry. And the key fact is the following theorem, that this octagon, I call this octagon for obvious reason, is exact if R is semi-local. And I should say that maybe I should add here that the case R is a field is known. And this was the result of Grenier Boli. I hope I'm pronouncing correctly, and Mahmoudi. I think from I don't remember the year. It's either the 2000s or the 90s. But the case where R is a field was known, and so this was it is actually true when the ring is semi-local. It is significantly more difficult to do this when the ring is semi-local, I should say. Some of this is because a lot of machinery, which is easy when the ring is a field is missing for semi-local rings. And the second thing, so what we show is we also show that when R is regular, so we can also define the Gersten-Witt complex. So we can. So here I have my Gersten-Witt complex, right? And you can imagine that each of these has a Gersten-Witt complex, and you get some kind of a web going to the center. And it turns out that the maps in the octagon, which I did not define for you, they are compatible with the differentials of the Gersten-Witt complex. And this is why we need this yet another definition, because the differentials in the Gersten-Witt complex, a la Balmer, Walter, and Gille, are somewhat implicit. So we needed something concrete to actually check this. So this thing is actually compatible with the Gersten-Witt complex. So this is what we're interested at, and this has half the degree. So there is room here for some kind of induction. So let me show you yet another diagram. Okay, so now what you see here is a big commutative diagram. So this is the octagon from the previous page, which I kind of spread it across a line. So now it's a periodic infinite line. And then I can base change to K, and I get yet another 8 periodic line. And then I can do the same for the, I specialize to every codimension 1 prime in R. And I do this, and I get yet another kind of line, another 8 periodic line. And finally, this is 2-dimensional, so I get this bottom line. So each of these, this is an octagon. This is an octagon. This is a direct sum of octagons, and so forth. And the thing is that the lines are exact. So all these lines, the lines are exact. And not the rows, I'm sorry, the rows are exact. Each of these rows is exact. So we know that the rows are exact. So now the question remains, are the columns exact, right? So let's see, what do we know? So this thing, all these rows, so let me circle the B's. This is exact by induction hypothesis. So I know that, so this is actually not yet enough. So it turns out that there is a famous purity result of Kolyotel and Sansuk for torsors over reductive groups over schemes of dimension 2. And this purity result, it can be restated so that it actually gives you that the columns are exact here and here and here. So this result actually gives you the exactness here. So you also have, and maybe I'll take it and do it in a different color. So this is also okay. So this is by this. And finally, we had to prove that this is exact at the end. I should say that Stefan Gille also gave a completely different proof for his complex of the same result. So we actually proved that the Gersten-Witt complex for any semi-local ring R is exact at the last term. So this is also exact at the end. So this is this you get from this. And this is enough. So this is enough to give you all the rest. So it's exact. By diagram chasing, you can show that everything else is exact. And this gives you that the Gersten-Witt complex is exact. And in particular, this map here is injective, so we get the Grothendieck and Serre conjecture for the unitary group of A and sigma. So I hope this was not too quick. I'm essentially finished.
Thank you very much. Let's thank a speaker. Is there any question? Any question? Any questions? If you would like to ask a question, just switch on the.
Yes, I do have a question.
Yes. Yes, sure. Go ahead.
Okay, so you, as I understood, this type of the proof you presented is a kind of very tricky in the sense that to prove injectivity, you prove exactness of certain complexes in other columns, not just injectivity. So you couldn't, as I understood, you are not able to deduce injectivity for given algebra A sigma if you know only injectivities for all other this B T tau, B1, T1, and dot, dot, dot. Am I right?
This is correct. Yeah, this is not enough. Yeah. So knowing that this is exact is in general not enough. Actually, you need every other part in this complex, essentially. So either these, well, in this case, it would be immediately done if you knew that it's exact here, or these. And in dimension 2, we have them. And there are some cases where this exact sequence degenerates, and this is how we get the results in higher dimensions.
And maybe the second question of mine is as follows. How does look like, how does it sound, this famous Grothendieck and Serre purity theorem?
How does it, what is it precise statement?
Yeah, right.
So I think what it says is that, okay, I will need another board. I see there is a question in the chat. I will answer it too. This result by Kolyotelen and Sansuk, forgive me for abbreviating, so that the X is a regular two-dimensional scheme, and I think G is a reductive group over X. And what it says is that H1 of so I think that the image of HXG. So inside, let's say that K is the fraction field of X, and let's assume that this is also integral. So this image is the intersection when I take all the codimension 1 points of X. So I take the intersection over the images of, so here I probably have to write OX P G into H1 K G. So I hope I remember correctly, but this is the statement. So you do not get the injectivity from their result, if that was your question. You only get that, you get, this is...
No, I wanted, and you gave me an answer. The assumption is very general, that G is just a reductive group over X. So it's not split, just anyone. Okay, yeah, thank you very much. Yes.
Okay, so there is a question in the
Yes,
chat.
in chat,
Yes.
yes.
Maybe okay,
I can read it. I see it. I can read it. So the question is, would the exactness of the Gersten-Witt complex of an Azumaya algebra of involution give the full Grothendieck and Serre conjecture for these group schemes? The answer is yes. So as soon as you know, you don't even need the exactness of the entire complex. You just need to know that it is exact here. Then you will get immediately that the Grothendieck and Serre conjecture holds for this group scheme. Well, I have to take a connected component, neutral connected component. And if you let A sigma vary over all Azumaya algebras with involution, then you will get all forms of GLN, SON, and SPN over your given ring R, whichever ring you managed to prove the injectivity, this injectivity for. Does this answer the question?
Yeah. So more questions? More questions? If not, then
Is there
there's a
something
question.
analogous for other groups? Something analogous to this approach?
I do not know. So maybe for the spin groups, you can do something because you have the fundamental ideal. Well, there isn't exactly a fundamental ideal, but you have invariance. So you can actually analyze the effect of these maps on these invariants, on the cohomological invariants that allow you to describe spin torsors. But I don't know. But beyond spin groups, I strongly doubt. This is something. Actually, I should say for SLN, this was actually done. You have the original Gersten complex, and you can get information about SLN. And I think this was done by Oren Guren and is it Panin? Forgive me for not remembering. So you can do something similar for SLN and the Gersten complex for the K groups, or maybe SK.
If A contains field.
Yeah, well, I mean, you have the complex anyway, and if you can prove that the complex is exact, you will get the Grothendieck and Serre conjecture. Yes.
Maybe this is a result of mine plus Suslin.
Okay, yeah, okay, yes. I'm sorry.
More questions? More questions? Any other question? So if not, then let's thank the speaker for a wonderful talk. Thank you very much. And so we will resume in a week. The next talk will be given by Sasha Kuznetsov. So we'll resume at the same time next Wednesday. Thank you very much, everyone. Bye.
Hey.
Thank you.